So before I just get stuck in then, obviously a lot of people have come to learn a bit about silicon MEMS printheads, and there's a lot of activity that's going on in the marketplace. We've got stuff coming out in the marketing of printhead vendors. We've got exhibitions coming up in ITMA, where people are talking about demonstrating silicon MEMS machines. And then I no doubt 2016 at Drupa, there's going to be also a lot of activity. So there's a real hive of stuff starting to happen around silicon MEMS. And certain companies are driving that and making things happen. So from Xaar's point of view, does that mean then is it all now about silicon MEMS? Why is this flurry of activity taking place? What is it about silicon MEMS? What is different about silicon MEMS to the printheads we know and that we use today? And what's better about them? And then probably the question therefore is that going to be therefore the end of the old type of printheads we're used to? Before I go into talking about the silicon MEMS side of the business, I thought we should talk a little bit about MEMS and some clarification. Clive, if you were at his presentation earlier this morning, he talked a little bit about what microelectrical mechanical systems are. We've got a slightly different view, really, in that we believe that there are a lot of MEMS devices out there. They are devices that are several millimeters down to a couple of microns. They're produced with various microfabrication techniques, not necessarily just silicon wafer processing, but they can be done through micro machining, grinding, laser fabrication, anything that produces a device at that sort of level. And MEMS devices split really into two sections. You've got what they call microsensors, and microsensors take mechanical energy and turn it into an electrical signal. And on the other side, you've got microactuators, where you take an electrical signal to turn it into a mechanical signal. I've put just up here, just for interest, I thought it was quite cool. Just got this from the internet. This is actually a MEMS device. It's not an inkjet device, but it's actually a little motor that spins. It's electrostatically driven. This is smaller than 0.5 millimeter in terms of width, with a spinning motor driven through electrostatics. So MEMS are really quite cool, interesting devices and very small. So by that very definition, I'm having a problem with my pointer. By that very definition, piezo inkjet printheads are microactuators. They turn electrical signals into mechanical motion that pressurizes a chamber to eject a droplet of ink. So in the case of Xaar, we've been making MEMS devices now for 25 years. Yeah, this device isn't working very well. Oh. Okay, so if we look at MEMS overall in terms of inkjet printheads, we sort of split the market up into two sides. So we've got what we call the traditional bulk piezo, and then the silicon MEMS that everyone's getting now all excited about. So if we look at some of the players, and again, Clive alluded to some of these this morning, there's obviously ourselves, there's Seiko, Konica, you've got Epson, who played around with piezo in the olden days in their inkjet printheads, Toshiba, Ricoh, Dynamatics, and Kyocera are all producing what we call traditional bulk piezo printheads. And if we look on the other side, the silicon MEMS, which we all think is pretty new, actually there's a lot. And it's been going on for quite a bit of time. So Epson being one of the people that have been producing silicon MEMS printheads for a long time. They're DX5 and desktop printers, and more recently, as Clive mentioned, the precision core printhead. Konica, obviously, who last year announced their silicon MEMS activity, and talking more about that through this year. Samba, which has been running at Dynamatics. Ourselves, which will be no secret, we've got a P4, what we call P4 program running, which is a silicon MEMS program. And then some interesting ones at the bottom here, where I put Canon and HP. Canon, really known for what they call bubble jet in your desktop printer, and HP call it thermal inkjet, where they make a MEMS device which doesn't have piezo, that heats ink, causing a bubble to be generated, and that then displaces the ink to fire out of the nozzles. But these are all MEMS devices, and I've just split them between what I call silicon MEMS and what we call bulk piezo MEMS. Some of these silicon MEMS, as I said, will drive with piezo, and some maybe with thermal. So again, you could recharacterize them differently as well. So going back to the original question about where we think different printheads will go, we need to look at the architecture to try and understand what the technology can do and what features it can bring, and maybe what some of the differences are between silicon piezo MEMS and the older bulk stuff that we have. So I've done a very simple schematic here. If you take a Xaar 1002, or for those who are not familiar with Printhead, and it's in this orientation firing downwards, and we were to cross-section it, this is the simple sort of schematic diagram that you would see where you've got the nozzles and they'd be firing downwards. The yellow is PZT material, piezo PZT material, and then we've got just a supporting top layer there. And what I specifically wanted to look at is if I took one of those elements out of that piece of PZT, and I apply an electric field to it, perpendicular to what we call the poling direction, then we get what we call a shear mode effect. So the PZT shifts and shears. Now, a lot of you may have heard Xaar talk about this before, but what's different? Well, why am I talking about it? Well, in this scenario here, you're allowing the PZT to move freely. There's nothing constraining or stopping it from doing what it wants to do. The PZT is, for a better effect, it's got no stress within it, no mechanical stress. So I'm waiting for this to catch up. Maybe the batteries are dying. So there you go, low stress. Low stress, obviously, in PZT means low fatigue, and if we're not fatiguing PZT, then it's going to last longer. And if we apply this element in this scenario, you can see the PZT is actually moving in the way it wants to move in shear mode. So in our traditional printheads, there's very low stress, very low fatigue, and this is why we get very long life out of traditional bulk piezo printheads, because of the shear mode activity. So if we then compare that, oh, sorry, one other thing to say when it pops up. One of the things to also comment on is that typically the thickness of these walls is about 70 microns. And if you're applying, as we do, around 25 to 30 volts across that, that's typically a field of about 0.4 volts per micron. And I'll bring that back in a minute when we compare it to silicon MEMS. Okay, so here's a cross-section of a generic thin film silicon MEMS printhead that's in the market today. And typically most of that is all silicon. So you can see there's much less piezo material. The nozzle plate would be made of silicon, the defining chamber walls are silicon, the cover at the top, and then what we've now called this thin film PZT, so very small layers of PZT on the top. In this, or in this type of technology, when you apply the electric field, you do it in the same direction of the poling. And what that causes the PZT to do is to shrink effectively and go fatter. So go thinner and go fatter, because the PZT wants to align to the electrical fields. So in that case, you can see how the shape, if I go backwards and forwards, you see the shape of the PZT is changing. That's the piezo properties of that material. However, when we glue this or bond this to the top of one of these chambers, you can't now allow the PZT to compress, because the edges and the whole thing is bonded to the top. So that means it's not doing what it naturally wants to do anymore. You're forcing a lot of stress, but you get this bending moment. So you end up with a curvature, and this bend is the thing that pressurizes the chamber. But the thing to say is that within the bend mode, it's high stress and high fatigue for the PZT in the bond layer. So it's very different to the shear mode architecture I just presented in the bulk. And there you go, it's just an example of firing that. These films, as we heard from the Ricoh guys, can be as small as a couple of microns. And again, if you're applying a similar voltage of about 20 to 30 volts across them, you end up with 10 volts per micron. So compared to the 0.4 volt per micron I spoke about earlier, that's a big change in electric field within the PZT material. Again, something, as you use it more, it will age it. So one of the things you'll be familiar with, therefore, is that, for example, Epson printheads using your desktop printers and in some industrial wide format graphic applications, they tend to have a much, much shorter life. People will talk about 6 to 12 months, depending on ink and application, compared to the multiples of years that we're used to from a bulk Piezo product. So if we go through and compare, I've put here, and we'll build up a table. Piezo mode displacement, we've got shear versus bend. The benefit is the green ones with bulk, and we're saying low fatigue, longer life, and that helps with the whole total cost of ownership of the printer and capability to print. So I've just pretty much just ruined everyone's thoughts, I guess, around silicon MEMS and what we're going to now do in the future. So I need to probably put that in context and talk about why the industry is looking at silicon MEMS. So if we then look again at the cost sections and we look at the volume, you can see here, so we've got big PZT walls, 70 microns thick versus a couple of microns on small areas of PZT. And so the volume is hugely different, and PZT is one of the most expensive parts in a printhead. So you don't want to put a lot in there if you don't have to. So thin film uses much less PZT. That's one of the better features. Come on. So I've just compared here. Typically, for Xaar now anyway, we're around 2 to 5 milligrams of piezo material per nozzle, where I think if you look at some of the silicon MEMS devices, you're like 1 to 2 micrograms of PZT material per nozzle, so a huge difference in terms of PZT. And just to put that into context of why that's such a significant change to where bulk has been, if you look over the years, so when back in around the late 90s when Xaar was first releasing some of its printheads, you've got about 30 milligrams of PZT per nozzle. And over the years, we've obviously driven to reduce that, to reduce the cost, to make it more cost effective, especially as you put more nozzles together in a printhead. And we're down there now to sub 5 milligrams per nozzle. But you can see the curve. It looks like it's now starting to flatten out. It's going to be probably tough to push it down much further in bulk. So you've got to sidestep. You've got to go to something different, and obviously thin film allows you to do that. So what are the features? Let's look at the sizes. So pitch-wise, you see here we're talking about in bulk around 141 microns. People are working to get that down, but typically you can get down to about 50 microns. So what that means is that your nozzles per inch in your row of nozzles is much closer together, and you can go from something like 180 native to 360 native resolutions. So I've just updated that there. What does that mean? So as well as going in the nozzle row orientation, you can also effectively do it in both axes. So you can add nozzles not just in the row, but you can add multiple rows next to each other. So you're actually putting 4 times the density of nozzles within the same area. And that means you can have a much more compact printhead and a much more compact print zone. So if we look at the PZT or the piezo material with respect to its location, in the bulk mode, the PZT is defining the fluidic chamber. In thin film, the PZT is outside the fluidic chamber. What that means is then the electrical connections that provide the electrical signals to the PZT are also outside of the fluid chamber. And that's one of the challenges about putting conductive fluids like water in this type of architecture. This naturally is very well set up for it. So, feature and the benefit, piezo position inside the ink path, outside the ink path, means our electrodes are also outside the ink path, means that we can now start to better handle conductive fluids like water. Right, there we go. Firing nozzles operation. So again, Xaar is well known for what we call its shear mode shared wall architecture. And if you compare that to silicon MEMS, when it comes up, maybe I need to get closer. There we go. You can see here that these walls, the PZT, are busy firing this chamber. That means I can't fire these adjacent chambers in this architecture. This is what we call shared wall. So we get around that by having what we call a three-phase cycling routine, where we fire every third nozzle, then go back and fire the other ones. But that sort of cuts our firing frequency down by a third. So that slows us down in terms of firing frequency. With silicon thin film, obviously, the PZT can do what it wants out here without interfering with the neighbouring channels. And that means you can just fire all nozzles at top speed together, in theory. So that gives you a much faster firing printhead than you get with bulk. So I've just put here active shared walls, yes, no three-phase firing, 3 times the speed. So again, we're building up a much greener picture now for thin film silicon MEMS. This final one really is just, I think, pretty obvious. I've covered it. And if you just look at the chamber sizes, they're much smaller. And again, that relates to being able to pack more in a much closer space. The pitch leads to that, but also the chamber size here is much, much smaller, so we can put more in a more compact space. So where does that get us? To a situation where we've got all these great features that we think are much better than the current bulk product, but we've got this big elephant in the room in terms of lifetime. Let's look at some of the other things outside of the printhead about manufacture. With our bulk piezo printheads, these are channels that are mechanically sawed at Xaar in the bulk, and you can see that we saw one at a time, and that's a slow serial process. It has high processing costs, and actually the resolution and the size of these walls are close to what you can do with CNC micromachining. So it's, it does its job, but will it be able to push it very much further? We're starting to see challenges there. The nice thing about it has low capital costs compared to photolith fabrication lab for silicon. It's much, much cheaper, but some of the downsides, you've got to cut away that piezo and you have large PZT wastage. So manufacturing of silicon MEMS, so that uses a silicon wafer fabrication process. It is highly accurate. It obviously generates very small features. That's what we need. And it's very repeatable. All the parts are the same. And the thing you'll notice when you produce a wafer like this, you get many parts per wafer, and that's what they call parallel processing. So it's good for high volume. It keeps the costs down. It keeps variability down, but you do have high capital investments. So you have to deal with a silicon fabrication facility. Summarizing, if we compare all the differences, you can see here that we've got a lot of green, but the elephant in the room, as I said, is around life. So what does that mean moving forward? So if we've got this issue of life, it means we're going to have to change the printheads more often. If we're going to have to change the printheads more often, the printheads need to be cheaper, because people are not going to want to pay the same price they do for the longer life heads. If you're changing the printheads more often, you're going to have more downtime potentially associated with the changeover of the printheads. So you need to make sure that happens quickly, because otherwise you start adding cost from downtime. So life is really important in silicon MEMS. It's something we really need to think about and how we position it versus the bulk. Printhead replacements need to be really quick and really easy so that you minimize the downtime. And printhead price is going to be key to balancing the books in all of that. So to make sure you get your total cost of ownership working. So is it the end? I don't think so yet. I think there's still the issue of life and potentially initial costs as people start to produce small volumes and start ramping up on silicon MEMS printhead. So I think bulk will still be around for a bit, at least. there's going to be markets and applications for both in the meanwhile. Certain applications will want long life, some will want shorter. So that leads us really to, why am I talking all about this? And why do we care? So this is probably the bit that I think a lot of people will be interested in. We've obviously been running our own silicon MEMS program now effectively since 2010, where we've been working on silicon MEMS development. This year we ran some successful in-house technology demonstrations to some potential partners, and just to get some feedback and prove to them where we'd got to. And then we intend to demonstrate this at Drupa in 2016. So if people would like to come and see that, that's hopefully a place where you're going to come and see this first Xaar silicon MEMS printhead. Name and a couple of little top-level specs. Xaar 5400, it's going to have over 5,000 nozzles. It's going to be 1 or 2 colors per printhead, giving you at a resolution of 1200 or 600, depending whether you use it 1 or 2 color mode. So I'm afraid I can't tell you any more than that at this time, but it just gives you an idea of where we've got to and what we're doing and what we're thinking about. So thank you very much for listening. If there's any questions, I'll try to answer the ones that I can.